Students, this is Dr. Church, and we're going to talk a little bit today about the mysterious and magical world of electric charge. Probably not the easiest subject to grasp, but one that's around us every day. We're affected by electric charge, even when we don't realize it. But everybody's familiar with static electricity. And if you think about objects that have an electric charge and why they have that, that's what we're going to talk about just a little bit today. So electric charge and static electricity. Well, if you remember from our studies from a while back, an atom has a nucleus, which is constructed of protons and neutrons, and around that in those outer shells are electrons. We know that protons are positively charged, neutrons are electrically charged, so a positive sign and a negative sign. What is the law of electric charge? Well, again, this is a little bit of review, but like charges repel, opposite charges attract. Positive repels positive, negative repels negative, positive and negative actually attract. Protons are positively charged, electrons are negatively charged. They attract one another and repel themselves, basically. Not sure exactly why that happens, but that is the law of electric charges. If we had two objects kind of suspended here so that they could move freely in space, we would see that objects of same charge would repel and opposite charges attract. Well, we can actually also calculate that force of attraction or repelling between those two charges. Now, we're not going to get into the actual use of this calculation. If you take physics next year, you would go ahead and calculate some of these forces that are acting between charges. But what I want you to know is that the magnitude of the force between two charged objects really depends on the electric charge and the distance between them. So that's the main thing I want you to know. Here's the governing equation, but again, don't worry about that too much. But there is a force between charged objects or charged particles, and that force is a function of the size of the charge, how much electric charge does it have, and the distance between them. Now, objects will produce an electric field around them. So that electric field does not extend forever. It will have what we call field lines. It has a certain shape depending on the type of charge and how the charge is distributed on either the particle or the object. And then that field, that electric field, will surround those objects in a region. And so those field lines have direction based on the flow of charge. And again, those are some issues that you would pick up in physics, but for our purposes, just know that electric charges have a field around them. Now, atoms do not have a charge because of the number of electrons and protons cancel each other out. That's under typical case scenario. So remember that the number of protons determines the atom, and the number of electrons will equal the number of protons in just a normally non-charged atom. But atoms don't always stay that way. What happens is they can gain or lose electrons. Now, they cannot gain or lose protons because the number of protons determines the element. Remember that from our studies in chemistry. But you can gain and lose an electron. So remember, we studied certain types of bonding. We actually learned about that in ionic bonding, the gaining or losing of electrons. And so here's an example. If we have 3 protons and 5 electrons, this actually has a net negative charge because you've got more electrons than protons. Now, if you had, say, 7 protons and 2 electrons, this would have a net positive charge because you have fewer electrons than protons. But again, you don't gain or lose protons, you gain or lose electrons, and that's what gives a particle its charge. Now, there are 3 ways that an object can be charged: friction, conduction, and induction. Okay, remember, Only electrons move. Protons stay right where they are. So you got friction, conduction, and induction. Well, let's look at friction first. Charging by friction is when we wipe two objects together, when two objects rub against one another. You've seen this. We were in the classroom today. Then we would do an experiment with this, and we can see that charge build up. Like if you I'm sure you've rubbed a piece of cloth on a plastic ruler or a glass rod or the rabbit fur on a rod, and you can see that there is a charge that that object picks up. And what's happening is that friction will either wipe electrons on or wipe them off, depending on which way they go, and that will give it a net charge. The other way is by conduction. Charging by conduction is when electrons move from one object to another through direct contact. If you have touched a battery to your tongue, that's conduction. If you've grabbed a live electrical cord and got shocked, that's conduction. If you touched a charged piece of metal, okay, then that those electrons will move to you. That's conduction. What happens in a piece of wire is electrical conduction as electrons move along the wire. So you've got friction, you have conduction, and now you have induction. Well, induction is probably the hardest to understand, but you can pick up a net charge by moving electrons around. The electrons don't necessarily leave or gain, but they can actually move around. So this happens when we rub a balloon. If everybody's rubbed a balloon and it stuck it, made your hair stick up or picked up some pieces of paper with it, you charge the balloon through friction. But if you bring something near it, what happens is the net charge will push charges away, and that will induce a localized charge on the object. Again, that's a little bit hard to understand, but don't worry about it too much. Just remember your terms there: friction, conduction, and induction. Okay, those are the main definitions. Just get the terms down for now. Well, what about conservation of charge? What's happening? How does something pick up a charge? Well, as in many realms of science, there's a conservation principle that happens. There's a conservation of charge when you charge something by any method, no matter if it's friction, conduction, or induction. There is no creation or destruction. Charge is not created nor destroyed. It just moves from one spot to another. The numbers of electrons and protons that exist, they all stay the same. They just move from one place to another, and that's the conservation of charge. Let's wrap things up with just a quick look at static electricity. Static means still or stable, not moving. So static electricity is electric charge that is at rest on an object. Charges of static electricity do not move away from the object, they just stay as they are. But it's like those clothes that come out of the dryer. They've picked up electrons, electric charge through the friction motion in the dryer, and especially if it's very dry and that charge is not conducted through the air to some grounded object, you'll pick up that static electricity, which is electric charge that is standing still on some kind of an object. Well, that charge can be discharged, and this would be the loss of electricity when it moves from that object. And so you felt that too in the wintertime. Your body can pick up a static electrical charge as you walk across the carpet, and then you go touch a grounded metal object of some kind, and that charge jumps quickly from your body to that object, and you'll see it, and you can hear the pop, and if it's heavy enough, it's a large enough charge, it kind of hurts. Well, there are some really heavy duty static electricity charges that get formed, and one of those is lightning. When clouds move, they will pick up an electrical static electric charge, okay? And that's from the movement of winds and moisture and dust particles and other things that are in the air. So during a thunderstorm, water droplets, ice, air move inside the storm cloud, and they build up a negative charge often at the bottom of the cloud. Then this drives positive charges to the top of the cloud. As those negative charges come to the bottom, what that does is induces a positive charge next to the ground. So that's a charge by induction between the cloud and the ground, and that builds up a really large difference in the charge uh, forces, the charge. Oh my goodness, what I'm the the magnitude of the charge, or the size of the charge. All right, sorry, lost for words there. Then what happens is when that charge gets great enough, then it'll jump. It will jump. Different parts of the cloud will build up a high enough charge, and then those charges will begin to jump, and it's electrostatic discharge. Okay, and we call that lightning. So a couple of things about lightning, just a little practical application here. Its strike's going to go to the highest point and take the shortest path, the least path of resistance to ground, okay, to the earth. So anything that kind of sticks up is going to be an attractor to the lightning, and that lightning will jump to those highest points first. An example of that is a lightning rod on top of the building. They put that up there on purpose so that rod can conduct the lightning away from the parts of the building that could be damaged. Objects such as a lightning rod joined to the earth by a conductor, we call those grounded. That there's heavy duty electrical wires that will run from the lightning rod to ground, okay, and that will conduct the electricity, or the movement of electrons, away from the building. Now, when that electric charge goes to Earth, the Earth is so large that it'll just absorb that charge, and it doesn't really damage it or change the voltage, the potential of the Earth. Um, so that's basically how a lightning rod works. So this is just a little introduction to electrostatics, electrostatic charge. We've learned that there are three ways to build up a charge. We know that there's a law of charge that opposites attract, likes repel. We know that the atoms, the elements, the atoms within an object, they don't lose protons, else that would change the element. What they do is they lose electrons. Electrons move from one object to another, and that builds up an electrostatic charge and can set up electrical flow. An excess of electrons is a negative charge. Excess of positive, less protons. Sorry, less electrons to protons, that would be a positive charge. Okay, sorry. So anyway, as we look at this, we can see that it's all around us. These electric charges are all around us. But as you kind of get these definitions down, this will set the stage for some other things that we'll do later when we look at electrical flow. Oh, yeah, static electricity and electrical discharge, lightning, static from your finger to a doorknob. Those things that we see every day all around us. So that's practical application there, as you understand it. Well, I hope you learned something today, and you enjoyed the lesson.